Okay, dear student, let's see what is there in this question. A neutron of mass m confined within the nucleus of diameter d, ignoring the numerical constants, what is an approximate expression for the kinetic energy of the neutron? Okay, so they are talking about the kinetic energy, they're not talking about the uncertainty in kinetic energy. Still, let's see. So we know that we have to use the Heisenberg's uncertainty principle in this question, isn't it? And the another hint is that there is a Planck's constant every time in the numerator, which clearly shows that yes, we would be using the Planck's the Heisenberg's uncertainty principle. So it is like delta x into delta p is greater than or equal to h by 4 pi, and delta x can be written as plus minus d by 2 because it is confined in space. So that can be written as d by 2. This will be written as delta p greater than or equal to h by 4 pi. Now, okay, so the uncertainty in the position, some books are saying that they just take it as d, books take it as d by 2. According to me, it should be equal to d by 2, but still there is a confusion in the authors, those who are writing your books, like whether the uncertainty should be d by 2 or whether it should be plus minus d. According to me, it should be d by 2. But in this case, clearly they are saying that you need not to refer to the numerical constants, so we can ignore that whether it is d by 2 or whether it is d. But anyways, I've taken 2 here. So from here, you can clearly say that the change in momentum or the uncertainty in the momentum will be given by h by 2 pi into d. Okay, so up to this we can easily reach and easily do it. But what next now? Next is that we know that kinetic energy can be written as p square by 2m. This is a very important formula, and this formula we learn in the topic 2 mechanics or in A for the new students. Yes. So delta p is greater than or equal to this. Now, we want to substitute this delta P in the terms of kinetic energy to find the expression of kinetic energy. Now, the question is, how can we do that? Because from the point of view of uncertainties, we can write delta E by E is equal to twice of delta P by P, provided there is no uncertainty in the mass M. We can use this, but what about this thing? We are not interested in finding the percentage error in the kinetic energy or the uncertainty in kinetic energy. We are not interested in that. We are literally interested in an expression for the kinetic energy. Now what we do, so here is the crux of the question. This is the uncertainty in momentum, or you can say the change in momentum, which is final minus initial. In these cases, we just take up this one condition. Supposedly that the momentum, initial momentum of the neutron was 0. So the change in momentum will be equal to the final momentum. So we can say that yes, you are literally talking about P, momentum of the neutron, is equal to this. Isn't it? What I did, I just assumed like delta P is equal to final momentum minus initial. I just assumed the initial momentum to be 0. So this is what is written there. And now this P is now substituted in here. Or you can say that this value of P is substituted in the expression to find what is E. So E is equal to P square by 2m, which gives us h square by 4 pi square d square divided by 2m. So 2m. So 4 pi square and 2, they are the numeric values and you need to ignore them. So you are left with h square divided by md square. Clearly, A is the correct option here. And yes, it is the correct answer. This is how we do it. Even this question is having a very important concept, that how can you treat this delta P as P, and so how can you actually substitute the value of momentum in the terms of kinetic energy. Now that is a big concept. Students will be getting confused here. So this is something that you need to learn. Okay, dear students, this is Professor Varun. Thanks for joining. Thanks for watching. All the best. Bye. Please join the YouTube channel.